Okay, hello everyone again. So today we will proceed from the previous class, and in the previous class we had seen about CMOS logic circuits and how to design various gates using CMOS design style. Okay, and here uh, we will proceed further to see some other logic families. Okay, but before that, small thing to uh, uh, say small thing to say about, and this is about switch logic. Okay, so and we will see various types of switch logic, but for the formal definition of switch logic, uh, I can write switch logic. Okay, so we know that transistors can be used as switch. Okay, and here uh, transistors can be used as switches. Okay, and for the case here we will be seeing that most of the time we will be using MOS transistors. That is, if I am talking about here in about this in this VLSI, most of the time we will see the MOS transistors. We will not talk about BJTs, but rather we will try to design the circuits using MOS. Okay, it can be PMOS, it can be NMOS, any type, but we will see that the MOS transistors will be used as as switches, because we know that basically in digital circuits we have to switch between high logic and low logic. That's it. There are only two possibilities, whether a logic low level or a logic high level. Okay, so it can be done, or we can visualize this as a function of a simple switch, where the switch can have just two states. Okay, either an on state or off state, on off or on off. Okay, so on can be regarded as a logic high level, and off can be regarded as a logic low level. Okay, so just like diagrammatically, if I can draw uh, the diagram of a switch. Okay, if this is a switch, so it can be either on or it can be either off, right? It can be either in on state or it can be either in off state. So it means that there are just two states in which it can exist. Okay, and for achieving this function, this can also be achieved with the help of MOS devices. Okay, so that's why I'm saying that the transistors or the MOS transistors can be used as switches. Okay, as we know that this can also operate either in on state or in off state. Remember, when it is off, when it is conducting in off state, we call this as to be operating in cut off state. Okay, and when it is on, it can be either in linear or saturation. Okay, so whether it is linear, it is operating in linear region or in saturation region, it means that it is in on state, and if it is operating in cutoff region, it means that this is operating in off state. So this is regarded as off switch. Okay, so these two are pretty much similar to each other as far as functionality is considered. Okay, and although we can also use MOS as an amplifier, but here we are not going to bother about being MOS used as an amplifier, but rather how to use a MOS device as a switch. Okay, and uh, that's why this term is important here, that is switch logic. Okay, because with the help of switches we can construct many digital circuits. With the help of switches we can construct many digital circuits, and if there is some device which can be used as a switch, then we can construct the digital circuits using that particular device. Okay, and as far as switch logic is considered, okay, uh, you will find that the switch logic is based on, we will see these things: the pass transistor and transmission gate and transmission gate logic. Okay, so basically the thing is, whether we will study pass transistor or transmission gate logic, we will see that in all these cases, the device which is used would be the MOS device. Okay, and this MOS device will be used as a switch. Okay, so whether it will either work in on state, or it will go in off state. Okay, uh, so let's start with the next topic, that is pass transistor logic. Okay, pass transistor logic. Pass transistor logic. Okay, so we already know that here we will be using MOS transistors, although everywhere MOS transistors will be used. Okay, but a pass transistor usage is a bit different from from the way it was used in CMOS. Okay, we saw that in CMOS logic style also the MOS devices were used, and here also we will be using the same MOS device. Okay, but the way in which it is being used here would be different from the way it was used in CMOS design style. Okay, we will see what is the difference basically. And remember that the way it was used in CMOS logic style, the most simple case was that of an inverter. For example, I am drawing it here again. Remember, this was PMOS and this was NMOS, and remember where we are applying the input, at the common gate, and we are taking the output from the common drain. Okay, and this was the power supply and this was the ground. Okay, so remember the way in which it is being used. Okay, so we are requiring the extra power supply here that is connected at the source of PMOS. Okay, and the source of NMOS was connected to the ground. Okay, so this is how we used the devices in the case of CMOS logic. Okay, now we will see how to use the the MOS devices in the case of pass transistor logic. Okay, so let me just rub this part. Okay, so basically just for example, if I am using a N MOSFET here, for example, if this is one N MOSFET. Okay, so look at this, how to use a transistor as a pass transistor. Okay, and let's say this is the gate. Okay, and these are the two terminals, source and drain. Okay, and let's say this is connected to some logic A, input A, and here another logic level B is provided. Okay, so the output will be taken from at this. Okay, output will be taken at this, right? And depending on the state of mode of operation of this MOSFET, this either this input A will be transferred to the output or not. Okay, so A can be either a 0 or a 1. So if A is, suppose if the device is on, then A will be passed to the output, and if A is 0, output is 0, or if A is 1, output is 1. Okay, so look at the difference in the way it is being used here to pass a signal between drain to source. Okay, between drain to source. Okay, and how it was used in the case of CMOS design style. Okay, so just let me give you a small example. Suppose, look at here, this is one NMOS. Okay, and this is the second NMOS, right? And connecting these two outputs, and let's say this is some input A, this is some input B. Okay, and this is B, and let's say this one is B bar. B bar means the inverted form of B, that is not of B. Okay, and this is some output, let's say Y or F, and then we will try to establish that what is this structure actually performing. Okay, so here the number of inputs are 2, the input A and input B. So I can draw for the sake of, let's say, truth table. So we have 2 inputs A and B. Okay, and the output is F, right? So we can have 2 conditions, sorry, we can have total of 4 conditions: 0 0, 0 1, 1 0, and 1 1. Okay, so let's say when A and B both are 0, so okay, so if this is 0 and this is 0, B, and B is 0 means B is 0 means okay, this is 0. Okay, and this is B bar, so B bar means it gets inverted and a 1 come here, 1. Okay, now the devices will be either on or off, right? Okay, now since these are these are NMOS devices, okay, and we know that when we apply a high voltage or a logic 1 at the gate terminal, then the device gets on. Okay, so for this case, this device, this NMOS will be off, because at the gate we are providing a logic 0, so this device will be off, and this MOS device will be on, right? So it means that this is not conducting, but this one is conducting. Okay, so this B input will be passing to the output, as this device is on. So B is 0, so it means that a 0 logic will pass to the output F, and F becomes 0. Okay, okay, let's look at the next condition. A is 0, B is 1. A is 0 and B is 1, B is 1. Okay, so if A is 0 and B is 1, okay, so it means that this B becomes a 1 here, and this is B bar. So 1 bar means this the gate voltage becomes 0. Okay, and A is 0, B is 1, B is 1, so this also becomes 1 here, right. Now under this condition, which MOS is on? The gate voltage is high for this upper MOSFET, so this device is on. Okay, this device is on. I can write here, this device is on, and the gate voltage is connected to a logic low level here for the lower device, so this device is off, this device is not conducting. That means that this path is not available, but this path, this device is available. So this will pass the input A to the output F, and the value of input A is 0, so this 0 will pass to the output F here via this path, okay, via this path, like this. So the value of output F becomes 0 here. Okay, similarly I can also show that when A is 1 and B is 0, F will again be a 0 here. Okay, now the last case, when both are 1, when A and B both are 1, let us see then what happens in that case. When A and B both are 1, so A is 1 here, B is 1 here, this becomes 1, and this is B bar, this becomes 0. Okay, so in this case, this device is not working, not on, this device is off, and this device is on. So it means that A is passing to the output via this MOSFET, and the value of A is 1. So in this case, the value of F becomes a 1 here. Okay, right. And what is this truth table indicating? That F is equal to, look at this condition, last case, the last term A dot B, that is A and B. Okay, so I can write that this is a circuit of AND gate which is being constructed using pass transistors, using NMOS pass transistors, right, using NMOS pass transistors. Okay, now similarly we can also construct AND gate using PMOS pass transistors also, right, in the same way. Okay, knowing that the functioning of PMOS is opposite of the way the NMOS functions. So you will have to think about it a bit, that how to connect the two PMOS transistors so that it will act as an AND gate. Okay. Okay, so so this is how we use pass transistors, and look at the way, if you can differentiate it from CMOS logic design style, where we remember we in CMOS logic design style we had one pull up network. Okay, just in the previous class we had seen this, and we had one pull down network, remember, and this was the output. Okay, and inputs were fed here at the common gate. This was VDD and this was ground, right. And if you can remember how many transistors were being used for constructing one AND 2 gate, so 2 transistors would be required for pull down network, and 2 MOSFETs would be required for pull up network. So total of 4 MOSFETs would be required for constructing one AND 2 gate using CMOS design style. But here assuming that the inverters are available, okay, the number of transistors are required are just 2, 1 and 2 here. Okay, 1 and 2, and if you want to include this inverter also, then you can add the number of MOSFETs required to produce one inverted output. Okay, And since these are small gates, so you will not notice much. You may not be able to appreciate, you may not be able to notice the much uh, the advantage that uh, pass transistors gives us in terms of number of transistors being used. So, but as the circuit grows bigger and bigger, then definitely it's going to save us more number of MOSFETs. Okay. Okay. So let us look at one more circuit. Uh, this is the first transistor. Okay. And this is the second transistor, and this is the output. Okay. And let us say that mm, this is B bar. Okay. And this is B, and this is A, and this is B. B. Okay, just let me change somewhat in this. B bar B, A. Let's make this as A bar. Okay. So this is A, this is A bar, this is B bar, and this is B. Okay. And the circuit, the structure is same as that of the previous AND 2 gate. Okay. AND 2 gate. Okay. Now, but what is the functioning? Is the functioning going to be same for this case? So let us try to establish the function to find out the functioning for this particular structure. Remember, we have two inputs, A and B. Okay. So we can have 0 0 0 1 1 0 and 1 1, 4 possible conditions, and the output values will come accordingly. Okay. So let's start with the first condition. When A is 0 and B is 0, B is 0, right? So A is 0, so A bar becomes 1. Sorry, this will become a 1 here. Okay. And B is also 0, so this is 0, and B bar will become 1. Okay. Now in this case, this transistor, let me name the transistors. Okay. This is, let's say, this is MOSFET 1. So let's say this is M1. This is MOSFET 2, M2. Okay. So in this case, which one will be on, M1 or M2? M1 is having a gate connected to high potential, so this will be on, M1 will be on, and M2 will be off, right? So M2 path is not available, so M1 path is available. So signal A will pass through M1 to F. Okay, and the value of A is 0, so F will become 0 here. Okay. Now going to the second condition, when A is 0, B is 1, so A is 0, A is 0, so this will change. B is 1, B is 1, A is 0, so A becomes 0 here, A becomes 1 here, A bar. B is 1, so B is 1 here, and hence B bar becomes 0, right? In this case, again, M1 is off and M2 is on, right? So M2 path is again available here, M2 path is available, and signal A bar will pass to F, and the value of A bar is 1, so the value of F becomes 1 here in the truth table. Okay, now here when A is 1, B is 0, let's see what happens. A is 1, B is 0, so A is 1, A bar becomes 0, B is 1, okay, B is 1, so B bar becomes 0 here. Okay, so again M1 is not conducting, M2 is conducting, so A bar value will pass, which is actually 0, to F via this path. Okay, and F becomes uh, 0 here. Okay, just a small mistake that I have done here, that in this case B is 0, right? B is 0, so this is actually 0, this is 0. Oh, let me do it again. A is 1, A 1, A bar 0, B is 0, so this is 0 and B bar becomes 1. Okay, so actually this M1 is available, M2 will be off. Okay, so M1 is on, so A will pass to F and the value of A is 1, so in this case F is actually 1. The last condition, when both are 1, A and B both are 1, let's see what happens. A is 1, A bar becomes 0, right? B is 1, so B bar becomes 0 here. So which one is available? M1 is off, M2 is conducting, M2 is on, so A bar, that is 0, will pass to F and this will become 0, right? Now what is this truth table? What is this truth table indicating at? Look at this. F is equal to A XOR B. A XOR B. Okay, so this is the case. This is the circuit for an XOR 2 gate. XOR 2 gate. Okay. So this way we can use pass transistors to construct various circuits. Okay, and these are pretty simple to construct with. Okay, and one instant advantage is that this will use lower number of transistors as compared to CMOS logic style. Okay, so some points regarding this. This can be used as an alternative to CMOS logic style. Okay, and the advantage is that the lower number of transistors are required. Lower number of transistors required for constructing the circuits. Okay, and how many number of transistors required, you can see from the circuit, you can see from the diagram. So for example, for AND 2 gate, including the inverter also, 4 number of transistors were required. Okay, for example, I can write here that for AND 2 gate, 4 transistors required. Okay, as compared to 6 transistors required in CMOS design style. Okay, and you can compare actually with the other gates, for other gates also. And the disadvantage is that which is actually a big disadvantage, a very big disadvantage, is that we cannot cascade the pass transistors. Okay, we cannot cascade. And why we cannot cascade pass transistors? There is a very big reason behind this, and we will see that thing also. Pass transistors gates cannot be cascaded the handwriting is not coming up to mark. Okay, I will try. Cannot be cascaded by connecting the output of a pass gate to the input of the next gate. Okay, and why can't we connect pass transistors in a series fashion? Is because the output voltage gets degraded. Okay, in the case of NMOS or PMOS, when they are being used as pass transistors. So let us see. And but it was not the case when we used this thing when we constructed using CMOS design style. But here when we use pass transistors, okay, for constructing gates using pass transistor logic, we should take care of this thing in mind, that we should not cascade the number of stages, more number of stages. We should restrict the number of stages being cascaded to up to 3 or 4 maximum. We should take this point in mind. So we should not connect many number of stages in series with each other, because there is a voltage drop. As the voltage becomes weak as it passes between input to the output. Okay, and the reason behind this is that, let us take the N MOSFET case. Okay, the N MOSFET case, and the point is that this N MOSFET is good at passing a strong 0. So I can write here that it passes a strong 0. 0 means low logic. Okay, but weak 1. Okay, weak 1, that it will pass logic high value, but as the logic high value passes through NMOS pass transistors, the value gets degraded. Okay, NMOS passes a strong 0 but a weak 1. Okay, and similarly for PMOS FET we can write, while PMOS pass transistors pass a strong 1 but a weak 0. That is the complementary operation. Okay, so this is N MOSFET is passing a strong 0. Okay, and P MOSFET is passing a strong 1. so they are acting in complement to each other. So let's see how does this thing happen. For example, when we take the case of a n MOSFET pass transistor, so if this is NMOS, if this is NMOS, okay, and this is gate, this is, let's say this is drain, this is source, and generally we take the lower potential terminal as the source terminal, right? Okay, so let's assume that in this case the gate is connected to the power supply or logic high, that is VDD, okay, and we know the condition for operation of n MOSFET. Okay, the n MOSFET will be on only if the gate voltage is higher than the threshold voltage, the first condition. Okay, that is VGS should be higher than, at least higher than, the threshold voltage of the n MOSFET device. Okay, this was the first condition, if you remember from the IDVD characteristic of n MOSFET, right? And what was the second condition for the n MOSFET to be in on state? If you can remember, let me just we can write that was to be able to operate in linear or saturation mode. Okay, and but this was the basic condition, that this implies that the n MOSFET is actually switched on, this is switched on. Okay, and if it is not satisfying this condition, that means this n MOSFET is basically switched off, right? Now if it is switched on, it can be in linear region or it can be in saturation region, right? That is one thing. Okay, now let's say that the drain terminal is connected to some potential, let's say logic 1. Logic 1 means it is connected to the power supply or the VDD. Okay, and in this case the n MOSFET is operating in on mode, that is it is actually on, and hence it will pass the drain terminal voltage to the source. Okay, and in this case this is actually the source terminal is the actually that terminal where we are taking the output from. Okay, so if this is the general condition, then the voltage at this source would be the voltage that is present at the drain terminal, because the pass transistor is on, and it will be equal to VDD. We can write that output would be equal to VDD. Okay, this is the case that we had seen till now. Okay, but there is a twist here, there is a small twist here. Okay, and because we know that this condition has to be satisfied to make the transistor on. Okay, and we also know that the gate voltage which was above the threshold voltage was called as gate overdrive. Okay, and the gate voltage should be at least threshold voltage of the device, so that it forms a channel, so that it starts to conduct. Okay, so it means that this threshold voltage value gets consumed by the device. Okay, and whatever voltage is available above the threshold voltage, only that particular voltage is actually being coming at the gate terminal, and we call that voltage at the effective gate voltage. Okay, so under this condition, the effective, what is the effective gate voltage? It is that voltage which is available above threshold voltage of the device. Okay, So this would be uh, mind it that the gate terminal is connected to VDD, the power supply, okay, and it is higher than the threshold voltage, okay, and at least threshold voltage is required to turn on the device. So the effective gate voltage that uh, appears to the device would be VDD minus VTN, where VTN is the threshold voltage of the N MOSFET, okay. So this is the effective gate voltage, okay, and in this case this N MOSFET is on because this condition is satisfied, that VGS is higher than threshold voltage, and this N MOSFET is on, okay. uh, and let's put some more condition, that initially Vs is equal to 0, okay, Vs is equal to 0, right. Now when the device switches on, this drain terminal voltage starts to pass to the source terminal and the source terminal voltage starts to rise, okay. So initially it was assumed to be at zero potential, okay, zero potential. Now the switch is on and this voltage is passing to the source voltage, and it will start to rise to VDD, okay, which is passing between drain and source, okay. This is the scene here, okay. Now when the source terminal voltage, that is Vs, reaches to VDD minus VTN, okay, because this, let's say this is the VDD mark, this is the 0 mark, so just below this VDD there would be some value that it will be VDD minus VTN, that is just below by the value of the threshold voltage, okay. So when the source potential, when the source terminal has reached just this level, that is at VDD minus VTN, okay, then if we calculate the value of VGS, what happens? VGS is actually can be written as VG minus VS, okay. What is the value of VG here? VG is VDD, and what is the value of VS here? VS is VDD minus VTN, okay, and this comes out to be equal to VTN, okay. So when the source is at this value VDT minus VTN, then the value of VGS comes out to be equal to VTN, okay, and we can expect that as the source terminal goes above this level VDD minus VTN towards VDD, then the value of VGS will drop below the value of VTN, okay. Is it clear? So again, when the source is at this level VDD minus VTN, the value of VGS is equal to VTN, okay. So obviously when the source terminal goes above this mark VDD minus VTN, then the value of VGS will fall below VTN, okay. And when VGS goes below VTN, that will indicate that the N MOSFET turns off, because this condition gets gets violated. Okay, so because we know that for turning a N MOSFET on, we have to have this condition satisfied. We cannot ignore this condition. Okay, and if the source terminal is going above VDD minus VTN mark, then VGS is going below VTN, and that will indicate that NMOS turns off. Okay, so what does these two cases tells us? This and this. So this tells us that the source terminal can reach up to a value of maximum of VDD minus VTN. So let me redraw this. So it means that the source terminal can swing between 0 to VDD minus VTN up to this value. Okay, and not up to VDD, and not up to VDD. This is wrong, because this will indicate, this will violate this condition. So this will be wrong. So it will only be able to swing between 0 and VDD minus VTN. Okay, under this condition. So what does it mean? The gate is at VDD, the drain is at VDD, but the source maximum is at VDD minus VTN. And but we wanted this source to be at VDD, the maximum, but we are not reaching to the maximum value, but rather we are reaching to VDD minus VTN only. Okay, and this is not, we are not able to satisfy. So it means that there is a degradation of the output voltage by a value which is equal to VTN, that is the source threshold voltage of the N MOSFET. Okay, so this implies that output level degrades by a potential of VTN. Okay, although you can argue that this will still be treated as a logic 1 value, we can say that this will still indicate a logic 1 value, but if we take this in terms of absolute voltage levels, then it will be definitely, it is definitely lower than VDD, and lower by what value? VTN. Okay, and this is just for the first stage, this is just for the one stage. Okay, what happens if we connect various stages? For example, this is one N MOSFET, this is M2, this is M3, this is M4, this is M5, let's say, and these are all connected like this in series. So what will happen in this case? Okay, so let's say all these are connected to VDD, this is VDD, this is VDD, all these are logic 1 level, all the gates are connected to logic 1, and this is connected to logic 1 again, that is VDD. So here a voltage drop, a voltage degradation of VTN will occur. Here 2 VTN voltage drop will occur. Here 3 VTN voltage drop will occur. Here the voltage will degrade by a value of 4 VTN. Here the voltage will degrade by a value of 5 VTN. So after each stage, the voltage level is getting degraded by a value of its threshold voltage. Okay, and for example, taking a typical case, if VDD is, let's say, 5 voltage, if VDD is 5 voltage, okay, and VTN is, let's say, even it's if it is 0.8 voltage, so after 5 stages it will degrade by a value of 5 into 0.8, that is 3.2 voltage. So it ultimately here it will appear 5 minus 3.2, that is 1.8 voltage, okay, which may not be treated as a logic 1 or logic 0. Which level? It may not be treated as a logic 1 level. Okay, so that is the issue here, that after each stage the voltage gets degraded by an amount which is equal to its threshold value, and after several stages it becomes a serious problem, and the logic level may actually switch and may indicate a wrong logic level. Okay, so that is the case here. So, and this is a very this is a pretty serious issue, because logic 1 gets converted to logic 0, which is entirely wrong here, entirely wrong, completely wrong. Okay, so this is one of the biggest drawback of pass transistor logic, that pass transistors cannot be cascaded by connecting the output of a pass gate to the input of the next gate. And remember this point, that n MOSFET passes a strong 0. Again, let's say because we have seen this, when it is n MOSFET cannot pass complete high logic 1, it gets degraded by VTN. Okay, so we say that it passes, n MOSFET passes a weak 1 value. That means that the output level gets degraded by some value. So actually logic 1 was VDD, but here at source logic 1 is coming out to be VDD minus VTN. So it becomes weaker as compared to the input signal. So that is why we say that it passes a weak 1, but as far as passing a 0 is considered, it is definitely going to pass the complete 0. Okay, it is not going to affect that 0 voltage level. So it passes 0 completely without any hindrance. So we say that the n MOSFET passes a strong 0 and a weak 1. Okay, and in the similar fashion we can establish that the P MOSFET would pass a strong 1 and a weak 0. Okay, so this is the case here, and to overcome this limitation, the next logic style would be used, that is a transmission gate logic style. But before that, you try to solve some problem based on pass transistor. Okay, just construct or 2 gate, let's say, and NAND 2 gate, NOR 2 gate, let's say X NOR 2 gate, using pass transistor logic design style. Okay, and one more homework I am giving here, that read from the book about complementary pass transistor logic, that is CPL. Read from the book. You may follow that book Kang that is given in your textbook. Okay, and you can also solve some more problems based on this. So next we will see the transmission gate logic. Okay.